Hello everybody, my name is Doron Nakar and I'm presenting you our research on surface roughness impact on the heat loss of solar vacuum heat collector elements, HCE. This research is in collaboration with Professor Daniel Feuermann from Ben-Gurion University in Israel. Let's start with summarizing our main research findings. The metal tube outer substrate roughness has a large impact on HCE radiative emittance and therefore on heat loss. The electropolishing process, in addition to proper grinding process, may little reduce heat loss values up to 2% only. Roughness average RA and roughness RMS RQ fail to correlate substrate roughness to radiative emittance and therefore to heat loss. The roughness slope parameters 1/ER or RMS slope R delta Q along with roughness height RZ show a good correlation to heat loss. No solar absorbance impact was noticed throughout our research. Let's try to answer why this research is important. The heat loss from a typical heat collector element is about 10% of the total annual solar heat absorbed at working temperature of 400 degrees C. The heat loss of an HCE with substrate roughness lower than 0.2 micron may vary between tubes up to 10%. Controlling the substrate roughness based on this study may reduce heat loss by 10% and therefore LCOE up to 1%. All the above findings are more important for higher operating temperatures. Let's have a look on HCE production flow and our experiment method. First, the mechanical grinding of outer surface of all tubes. Then we introduce an optional electropolishing process. Then the selective coating, the sputtering process, and then the final assembly and vacuum sealed of all tubes. And then the HCE is ready for the heat loss test. So by changing the substrate roughness at the first stage, we expected to see the impact at the heat loss test. The substrate roughness measurement was performed using a 2D stylus profilometer, as you can see in the bottom right photo. Each roughness profile was recorded from every measurement, and also over 30 parameters, as you can see, were recorded from each measurement. The parameters are usually divided into three main groups: the height parameters, such as RA, RQ, and RZ, the spacing parameters, such as RSM, and the hybrid parameters, which are the combination of the above two, such as R delta Q. The heat loss measurement is a common test used by HCE manufacturers. It's basically measured the electrical power needed to maintain the tube at 400 degrees C in our case. We use a single test bench located at indoor laboratory that has a repeatability of ±1.5%. A schematic diagram of our lab setup is presented. Results. The electropolishing process may reduce heat loss by up to 10%, but we found that refined grinding process can make electropolishing process unnecessary. The height parameters RA, RQ, and RZ are increased after the electropolishing process and therefore fail to correlate roughness to heat loss. In fact, the RA are increased by 25%, as you can see in the graph presented. The roughness slope, however, presented by 1/ER or R delta Q are decreased after the electropolishing process. Both parameters show good correlation to heat loss as presented in the following graphs. Since both ER and R delta Q are dimensionless parameters, they cannot represent roughness alone. Therefore, RZ is provided in addition to them. Surprisingly, R delta Q and 1/ER are very well linearly correlated. R delta Q is a more stable parameter, therefore is more recommended to be used. To summarize our talk, substrate roughness can be measured adequately by 2D stylus portable profilometer. Roughness slope 1/ER or R delta Q along with roughness height RZ show good correlation to heat loss for both cases, grinded only and grinded and electropolished tubes. Proper grinding process makes the electropolishing process unnecessary. No impact on solar absorbance, up to 1% improvement on total annual heat gain and accordingly lower LCOE. Larger impact on higher operating temperature is expected. Thank you for watching.